In this video on therapeutic ultrasound, I want to review the basic science, that is, the physics behind ultrasound and what ultrasound really is. It's important to understand the physics behind ultrasound, both to understand the research literature and also to understand the modality itself and to safely apply it. Ultrasound is a wave, and a wave is simply a means of transporting energy. There are different types of waves. Electromagnetic waves, like light waves, radio waves, microwaves, can travel through a vacuum. Mechanical waves and sound waves, even ultrasound waves are mechanical waves, need some sort of physical medium for transport. They can't go through a vacuum. So if you're as old as I am, you'll maybe remember the original Alien movie. The tagline of that one was, "In space, no one can hear you scream." That's because space is a vacuum and sound waves don't travel through a vacuum. By the way, this was an excellent movie if you want to be scared. There are two types of mechanical waves, longitudinal waves and transverse waves. In longitudinal waves, the displacement of the transport medium is in line with the direction of the energy transport, whereas in a transverse wave, the displacement of the medium is perpendicular to the direction of the energy transport. So in this image, the top image shows a longitudinal wave where the Slinky gets compressed together and then spread apart, but that happens along the Slinky the same direction as the line of energy transport. In the bottom picture, the Slinky is being shook side to side, so the wave goes side to side, but the energy transport, that is the direction of the wave, still goes down the Slinky. Longitudinal waves have compressions and rarefactions, and those occur as the molecules in the transport medium, whatever that is, bump into the molecules next to them and push them along. So in the picture here, you can see a compression where the coils of the Slinky are all compressed tightly together, and you can see a rarefaction where the coils in the Slinky are spread more apart. Sound waves, whether that's audible sound or ultrasound, are mechanical pressure waves. Sound waves are longitudinal in a gas or a liquid, and they're longitudinal in our bodies in the soft tissue. Sound waves can be either longitudinal or transverse in a solid. In this animation here, you can see the longitudinal wave and some compressions and rarefactions as that longitudinal wave is propagated through the medium. You can also see that even though the wave moves, there's some little red dots here that are in the transport medium, and you'll see they oscillate back and forth, but they don't actually move along with the wave. They more or less stay in the same place. Now we need to consider some things about how waves behave. One thing that can happen to waves is that they are reflected. Wave reflection happens when a wave encounters the end of one transport medium and the beginning of a different transport medium that is of a different density. And that change in transport medium bounces or reflects the wave back towards its origin. You'll be familiar with this if you've ever been at the edge of a canyon and you've shouted out, "Hello down there." And then you hear the echo back a second or two later, "Hello down there." That's the wave being reflected off of the far wall of the canyon because the rock is much denser than the air. The part of the wave that's reflected, so the echo that you hear back, may have the same speed and wavelength as the original wave, so it'll sound like what you shouted into Echo Canyon, but it will lose amplitude. That is, the reflected wave or the reflected sound will be quieter. Part of the wave might be reflected, and part may continue on as the wave moves across this boundary between the transport mediums. In this case, the wave speed and the wavelength are affected, as well as amplitude being lost. So if you were inside the rock in Echo Canyon, it would sound different than it sounds out in the air. The greater the change in the density of the medium, the more reflection occurs. That's why Echo Canyon works so well, is because rock is so much more dense than air is. So here's an animation of a transverse wave and wave reflection when that transverse wave moves from a less dense medium to a more dense medium. You see the wave comes from the left. When it hits that more dense medium, part of the energy of that wave is reflected back towards its origin, and part continues on through the more dense medium. So we've talked a lot about the behavior of mechanical waves. What I want to do now is to actually show you some videos of a Slinky and illustrate what those actually look like in real time.
Hit of the day when you're ready to play. Everyone knows it's Slinky. It's Slinky. It's Slinky. For fun is the best of the toys. It's Slinky. It's Slinky. The favorite of girls and boys.
So here we have a video of a transverse wave. You remember that in transverse waves, the displacement of the medium itself is perpendicular to the traveling of the wave. So in this Slinky, the displacement is side to side, but you can see the wave actually moves from one end of the Slinky to the other in a perpendicular direction to the wave. In a longitudinal wave, you'll remember the displacement of the transport medium occurs in the same direction as the wave movement itself. So here you can see the wave movement is going from left to right, from one end of the Slinky to the other end of the Slinky. The wave that's moving through the Slinky is a compression wave. So the coils of the Slinky get compressed, again, from left to right, or along the Slinky from one side to the other. Thus, we have a longitudinal wave moving through the Slinky instead of a transverse wave. On this slide, we're going to see a longitudinal wave that is then reflected when it hits a barrier or a change in density. So you can see the longitudinal wave comes from the left, moves through the Slinky, and then is reflected when it hits a barrier on the right side, just outside of the video frame. That's what longitudinal wave reflection looks like. That's what an ultrasound wave would do, for example, when it's traveling through the soft tissue and hits either more dense soft tissue or maybe hits bone. Here we again have a longitudinal wave. This time we have a density change in the transport medium. So you can see here we have some coils of the Slinky that have been held together with actually just a few binder clips. And when the wave comes from the left, when it hits that different density, that higher density, some of the wave is reflected back toward its origin, and some continues on through the transport medium. Waves can also be refracted. Wave refraction occurs when the change in transport medium actually changes the direction of the wave. So reflection happens when it bounces the wave back towards its source. refraction happens when it continues on, but it changes direction in the new transport medium. With wave refraction, the wave will change direction, speed, and wavelength. You can have some refraction and some reflection happening at the same time. In regards to ultrasound, this is just another way that the ultrasound wave can get scattered in the biological tissue that you're trying to sonate. And here's just a fun, nerdy cartoon about wave refraction. The caption says, "The principle of light refraction as demonstrated by an NFL lineman." So when he's out of the water, you can see that his finger has been broken, but when it's in the water, it looks like his finger's intact. Another thing that can happen with waves is that they can interfere with each other. So if you have two waves that meet in some sort of transport medium, any number of things can happen. If they are exactly out of phase, they'll cancel each other out where they meet. If they're exactly in phase, they'll add to each other or increase amplitude where they meet. So here you can see we're back to our Slinky, and we have wave interference happening with longitudinal waves. You'll see a wave come from each side, and watch what happens when they cross each other in the middle. So the wave comes from each side. It almost looks like when they meet in the middle, it bounces back, but that's not actually what's happening. Each wave is just continuing on its merry way to the other side of the Slinky, but right here in the middle, where they cross each other, you'll see that they summate, and you get kind of a really dark spot when they cross in the Slinky. And that darker spot when they cross in the Slinky happens because the compression of each wave summates, adds to each other where they cross, and you get a really highly compressed part of the Slinky as they cross each other, and then they go on their way and it's not compressed anymore. You can also have wave interference. For example, if you're on a lake and there's a lot of boats out, each boat is creating some waves, and then when the waves from one boat's wake interact with the waves from another boat's wake, you get some really tall waves and choppiness in the lake, which makes it hard to go skiing. So one of the things that can happen when you get wave interference is that if the waves interfere in just the right way, you can get what's called standing waves. And standing waves occur when the two waves interact such that the peaks and the troughs of each wave line up, and they cause a wave that doesn't actually appear to travel, but has a heightened amplitude. So here you'll see we have one wave up here, the blue one, that's going from left to right. We have another wave here, the red one, that's going from right to left. And below in the black, you can see we have the wave interference. What actually happens when you have two waves like that interfering with each other. And you can see even though the amplitude of each of the blue and red waves is about 4 little marks on our little thing here, the amplitude of the standing wave is double that because they've summated, and it goes to 8 little marks on the scale there. So standing waves will have a much greater amplitude because the sending wave, in this case the blue one, and the reflected wave, in this case the red one, add together and create this standing wave with twice the amplitude. So on the previous slide, we showed standing waves that were transverse. It's a little easier to see them when they're transverse that way. Here we have an illustration of standing waves that are longitudinal waves. So in this, the top animation there, you can see the longitudinal waves, or the compression and rarefactions. And what you have is that longitudinal wave going through the transport medium, hitting the boundary on the right, and then coming back. When they create a standing wave, it looks like that standing wave isn't really going anywhere, but you get these really big compressions and rarefactions in your longitudinal wave. The way this relates to ultrasound is it's a longitudinal wave, and if you get reflection, and that reflection happens just right, so you get these standing waves, you can see you're going to have a lot more compression and rarefaction. That is a wave with a lot more amplitude or energy than what you think you're doing based on the settings of your ultrasound machine.
Here's a real-life example of standing waves. This is from the Children's Garden at Huntington Gardens in Pasadena. Basically, it's a very large metal walk-shaped thing with a vibrator at the bottom and filled with water. You can see toward the edge, when the waves hit the edge of the container and are reflected, they generate standing waves. And sometimes those are actually quite remarkable. This is the same kind of a thing that can happen in ultrasound in human tissue when the ultrasound travels through the soft tissue, is reflected off the bone, and then interacts with that reflection to create standing waves. That, of course, is something we want to avoid because standing waves will be about twice the amplitude of the wave that's being sent.
And here are the references for this part of the presentation.